So I'm going to explain the gradient first, okay? So the gradient is actually, it's a vector. Okay, you have to remember that. You have to firmly remember that. Gradient is a vector, okay? Because it shows the direction of how fast it changes. So, one more, this is a vector, and you get it from scalar function or field. Okay, that's a, very powerful feature of gradient. Okay, you have a scalar function, and you get vector field, vector function. That's very powerful. Why? Because vector is completely, it has more dimensions, right? But scalar, it has less dimensions, right? So from smaller dimensions, you get bigger dimension. That means you get more information out of smaller ones. This is really important, okay? From scalar function, from smaller information, this is vector you get more information. That's almost impossible in normal sense, right? Right? But this is possible. This is a gradient. Okay? Physical meaning is rate of change. In this one gives the direction, rate of change. I'm going to explain more, but mathematically this is what it is. For writing, you get gradient, okay, grad f. F is a scalar function. This is a function that you know normally, right? So in writing, you can write this way. Gradient. F is a scalar, but this whole thing is vector, right? Then vector needs arrow, right? So I prefer to use this when you write in hand, okay? And another form is this, the inverse triangle, okay? That's called del or nebula. Okay, frequently del, you call it del, okay? So del f in writing. Okay? So that's the, mathematical notation of gradient. All right? And the definition is this. Del f is a mathematical operation, right? Del is this. Del is d over dx, d over dy, d over dz. That's the definition of del. This is a del operator. Okay, this is del operator, and the definition is this. So each component is partially differentiated with its own coordinates. Okay, so it's the d del f is df over dx, df over dy, df over dz. So it partially differentiates with its own coordinates. That's what this gradient is. Okay? You can write it that way. So we'll find it, from numerical values. That's easier to understand, right? So the calculation is not that easy. Not that hard. This is, so easy. Let's say. We have a scalar function like this. X minus 1. 4y minus 2. Let's assume that we have this scalar function. And we want to get del f, gradient f. Okay? And f is 4xy minus 2x minus 4y plus 2, which is c, right? That's the function. Okay? And then del f is partially differentiate this whole term, right? So df over dx is, we have 4y and we have minus 2 and there's no x term, so 0. That's the x component, right? And then the df over dy here, because it's a y coordinates, so y is 4x minus 4. Okay? So that's del f. So we have to find del. So del f is a vector function of x and y, right? So depend on the position P, the gradient changes. Okay? The gradient changes. So if we write it in, let's say, sorry. Okay, so we have to, this is the vector, gradient vector, and we have to visualize it, right? We can plot that, right? Like this. I mean, we can find the value depend on, the position, right? So that's what? -2 and -4, right? If we change 1, 1, that's 2, 0, right? So as position changes, the value changes, right? The vector changes. So let's try to show this on the plot. That's the plot. Okay? All right. So as C changes, you have changing the the height of the function. Okay? You're changing the height of the function. That's pairs of here, this one pair, this one pair, right? So C is C is from that way. C is getting bigger. Okay, so from the center, outer side, the C is bigger. Okay, top view X and Y. Okay, and you calculate all the values like this, right? And show it here. So actually, what it is this gradient is flowing like that. Gradient. Okay? So it's flowing like that. The gradient factor. Okay? That's direction. It's a kind of direction field. So you're gonna get more information out of this calculation. All right? And next. Okay. So I'm going to give you, 3 more, concepts about gradient. Okay. This is all about gradient. Okay. So you have to fully understand what gradient is. And I'm going to define a new name, directional derivative. Okay. This is a scalar. Gradient is vector, but directional derivative is scalar. From the name itself, it's kind of saying something about direction. Okay, so since it's a vector, this is one of another direction related things. Okay, so it's a directional derivative, and the definition is this. Okay, D, big D, and B is a vector that shows direction that we want. Okay, the B, vector B is, actually B is, unit vector. So I'm going to put, this one. It's a length is 1, right? It's a vector that I want, and that's the unit vector. Okay? And this is a function, right? So the definition is this. The unit vector that we want, dot product with gradient f. What's that mean? Okay, this picture shows that. Okay? So let's say we have, x, y, z. We have that, right? This is, that's f of x, y, z is f of x, y, z, right? For example. And that's the surface here. Let's say that's surface here. Okay? And if we, calculate gradient, that's gradient. At point P, that's gradient vector. Okay? And we don't want that the desired, direction is this. Okay? That's the desired direction that we want. And the unit vector in that direction is B. Okay? then what is the effectiveness of this gradient f in that direction? That is this, right? Inner product, dot product. When B is unit vector, the inner product between B and gradient f really shows you the amount, right? The length of that gradient vector projected onto the new line, okay? New direction, that's what it is, okay? And this is, if it's not, unit vector, you have to divide it by, its length, right? So that you can normalize that, right? All right, so f of x comma y comma z is 2x squared plus 3y squared plus c squared, and p is 2, 1, 3, and the direction vector a is 1, 0, minus 2. Okay? So let's get direction vector. So d, a, f of p. So it's a number. So we don't put, arrow on top of it, right? It's a number. So gradient f is, with respect to x, so it's a 4x and 6y and 2z. Okay? And gradient f of p, you plug these numbers in, and that's 8, 6, 6. Okay? So it has some direction already. Okay, at point P. And then A, this is not unit vector, right? So you have to divide it by its length. So dA f of P is A divided by A dot product this, right? So it's 1 over square root of 5, okay? And 1, 0, minus 2 dot product with 8, 6, 6, which is minus 4 over root 5. Okay? So the calculation, that's easy. You simply, apply the formula once you understand that, right? But you have to know the true meaning, the underlying meaning. That's the amount that you want, okay? This is the amount you're calculating. Okay, so you project, onto this line, and that's the amount that you get. Okay? Just amount, just the length, not the, direction. Okay? All right. Why don't you solve this? So you find the A F is, yeah. Gradient f is 4x 4y, right? And gradient f of p is, you plug that in, so you get 12. Sorry. You plug that in, right? Okay. And so DAF is 1 over the length of A, right, which is root 10, and minus 1, minus 3, and dot product with 12, which is 48 over 10. Okay? So if you draw that, always you should be able to draw it, right? Draw the graph. This is actually circle, center of y, and at P is like 3, 3, that's P, right? And A is something like that, that's A. And the gradient at P is this. Okay? So the gradient, from actually, this is the, tangential. So gradient is proportional, perpendicular to the tangential at that point. Okay? So I'm going to explain more, but you can remember that. All right? So, another understanding of gradient is direction of maximum increase. Okay? Gradient, if you calculate the gradient at point P, that shows direction of maximum increase. Okay? In that direction, there's a maximum increase of function. Okay? All right, proof, very simple. B is unit vector, right? And dot product with gradient f. Okay? So it's a dot product, so you get, length of each vector and times cosine gamma, the whatever, the angle between two functions, two vectors, right? Okay? And since the length of B is 1, right? This is a unit vector. So that's what it is. Okay, so the length of gradient vector, okay, times cosine gamma, and gamma is 0, then that's maximum, right? Meaning, B and gradient is the same, or the same direction, then that's maximum. It means again that gradient, the direction of gradient is the direction of maximum increase. So problem 24. Yeah. Let me explain it a little bit about this kind of problem set. Okay? Heat flow. What is heat flow? We believe, in this, space, in this classroom, the temperatures on each spot must be different, right? Probably, right there it's cooler because there's the air conditioning there, right? But it's, right there, it's kind of hotter than that place, right? So every, the positions in this space, the temperatures are different, right? And from physics, we believe that due to the temperature changer, the temperature differences, there's a heat flows. Okay? For example, if that place, the aircon place is cooler, and this place is hotter, then heat flows from here to there, right? That's how the heat flows. That's what we believe. Okay? And the temperature function distribution is given by this function. Okay? And we want to know the direction of heat flow at point P. Okay? 자, 이 문제는 약간 물리 문제에 가까운 얘기죠. 만약에 우리 교실이 이렇게 돼 있다면, 여기가 에어 컨디션이 있는 천장이라면, 그렇죠? 템퍼리처가 이렇게 그러면 안 되겠다. 템퍼리처가 이렇게 돼야 되나? 그렇죠? 에어컨 있는 데가 제일 낮고 다른 데가 높겠죠, 그렇죠? 오케이. 만약 이렇게 돼 있다. 그러면 그 지점 2.5와 1.8인 지점에서 이때 그레이디언트의 방향이 어떠냐를 묻는 거예요, 이게. 그런데 만약에 이게 그러면 maximum decrease of t. maximum decrease라는 얘기는 뭐예요? maximum increase의 반대라는 얘기지. 그렇죠? 맥시멈 그레디언트 뭐였어요? 맥시멈 인크리즈였죠. 그죠? 그러면 맥시멈 인크리즈면 뒤쪽으로 이렇게 돼 있겠지. 이 서페이스의 노멀일 테니까. 아까 90도였을 테니까. 그러면 이거의 반대 방향이라는 뜻이에요. 그죠? 그쪽 방향이 힛이 그쪽으로 흘러간다는 소리예요. 맞죠, 우리? 그쵸? 네, 여기서 이렇게 가야지. 그쵸? 네. Okay? Alright. So, calculation is easy again. Alright? Just gradient. T. Okay? So that's minus 6x, 4y, and at point P, it's minus 15, 7.2. Okay? If you draw that, actually that's here. Alright, so P is about 2.5 here, 1.8, so that's P, right? And you have to go minus 15 and plus 7.2. So minus 15 to here, about here, right? Minus 15. And 7.2 to the positive side. I don't know. Maybe around here. Okay? That's the direction of heat flow. The last one, last concept of, gradient. We need to know more about gradient because gradient is so important, okay? So that was first, it was what it is the direction of rate of change, okay? And directional derivative, we use, gradient for the getting, directional derivative. And it's the direction of maximum increase, right? We verified that. And the last, property or feature of gradient is it's a normal vector to the surface. Okay? If you have a surface, if you get a gradient, that shows the normal vector. Okay? Let's see. Okay? So let the function of x, y, z. Okay? Then you differentiate it. Okay? Then df over the partial df dx times the total dx dt because x is function of only t, right? Okay? And you do that, right? This is a chain rule, right? So this is differentiation chain rule. And since there's a c, if you differentiate it, it becomes 0. Okay? And let's investigate this term. This is nothing but gradient f dot product with r prime, right? When r is that. This is an interpretation of multivariable, I'm telling you again, multivariable to vector. Okay? So it is kind of extending or using, multivariable calculus to, vector. Example 2. Okay, so we have the following function. Z square is 4 times x squared plus y squared. At point P, 1, 0, 2. Well, let's draw it. Let's graph it. Okay, so it's a x, y, yeah. So it's like this cone. Its shape is this cone. Okay. All right. So point P is 1, 2. So 1 and y is 0 and c is 2. So let's say this is a P. Okay? Then the gradient vector at P is what? That's n. N is what? N is unit vector. It's a hat, so it's a unit vector. So it's what is it? So it's gradient vector f over gradient vector f. Okay, so it's gradient vector. So it's if we have gradient vector here, and it's unit vector of that, right? Unity of that. Okay, so calculation is easy again. F of x comma y comma z is 4x squared plus 4y squared minus z squared is c. Okay, and gradient f is 8x 8y minus 2z. Okay, the partial differentiation on each coordinate, right? So f of p, you plug p in, so it's 8 comma 0 comma minus 4. Okay, that's the direction of gradient f at point p. Okay, so that's what it is. Okay, and n vector, there's a normal vector. Normal vector, okay, is gradient f of p divided by gradient f of p is 2 over root 5, 0, 1 over minus root 5. Continue on problem 30. Okay, find surface normal. Okay, I'm going to solve it. So the gradient df del f is 8x 18y. Del f of p is 16 comma 6 over 56, like that. And if you draw that, so you have ellipse here. This is 3 root 2. This is 2 root 2, I guess. And p is 2 and 56 over, so it's like here. And the gradient has to be, something like that, right?